Father, thank you for this day. Thank you for letting us gather here in Kimona today. Please help that as we perform our labs, that we will be able to learn and understand what needs to be as we do information.
Thank you. Okay, we have a quote today from Brigham Young. Do you have something to share? I don't know. Okay. We have a quote from Brigham Young. Every discovery in science and art that is really true and useful to mankind has been given by direct revelation from God. We should take advantage of these great discoveries and give to our children the benefit of every branch of useful knowledge and prepare them to step forward and efficiently do their part in a great work. So, in case you were feeling like, why is it that we have to take chemistry again? Then this is our motivation, because this is helping prepare you to take, to do your part in the world. So that's why we're learning chemistry today. I think one of my best friends, her name is Betty. She's an ER doctor. Does anyone want to be a doctor? Anyone want to be an ER doctor? Maybe? They're like, no. Yes, one person. Good. Okay. It's good to be, want to be something else. But Betty is an ER doctor, and I was talking to her about chemistry and teaching like Chem 105, 106, 107, and a lot of students that would say, I don't see how chemistry is going to be relevant to my future life as a doctor. Has anyone ever, I won't hold it against you, had that feeling? Yeah, I understand. And sometimes it's good to learn things not because of their utility, but because it like helps you grow in some other way, like in your critical thinking or something like that, right? But actually, chemistry is one of those things that is very useful to her as an ER doctor. So she's told me stories about people who come into the ER and who are flatlining, like their heart isn't beating, and their blood has become acidic because the CO2 isn't getting released like it normally should, and the CO2 reacts with water to make acid, right? So because their blood is acidic, that's also sort of preventing their body from like waking up and doing what it's supposed to do, because it starts to mess with things, right? All of your proteins and whatever. Anyway, she's told me the stories of having someone come into the ER flatlining, and she sees that their blood is acidic, and she injects them with sodium bicarbonate. Why would she use sodium bicarbonate? Because it's a what kind of thing? It's a base, right? So it's going to neutralize the acid and help restore their pH levels in their blood. And she's told me stories of people coming in, flatlining. She injects them with the bicarbonate, and they come back to life. And so when I asked her, when do you use chemistry in your job, she said, I save people every day using chemistry. And that's like one example of how she uses it. So when Brigham Young was saying we're supposed to prepare people to step forward and efficiently do their part in great work, this is one way that chemistry is preparing you to go forward and make a difference in people's lives and do good work in the world. Okay, we're going to start doing experiment 2 today. Did anyone feel like a little stressed or intimidated by the pre-lab assignment? Yeah. Now, I want you to know I wouldn't give you something to do if I didn't believe that you were capable of doing it, okay? And I know that you guys are all capable of doing it, and I also believe when you get into the lab and you have a chance to talk it through with your lab partner, things are going to start to come together for you. You'll feel a little bit more confident about that. Okay. Our learning objectives for today are to define the terms endo and exothermic and describe system and surroundings in the experiment. That's all sort of a review of things that you learned about in Chem 105. Then we're going to talk about calorimetry, how we can use calorimetry to find the heat of the reaction. And we're going to talk about Job's method, which is the method that you're using, varying the ratios of the reactants to find the stoichiometric ratio. And finally, we're going to talk about problem solving, which is your process skill for this week. So I have a demonstration here. Now normally the lecture prep people bring like an approved board, but I found this thing. I think it may be used to hold like tithing envelopes. And I just got it a little bit wet. I'm gonna get a little bit more water just on the bottom. Okay. I just got it a little bit wet, and I have this reaction that I'm gonna do with, this is some barium hydroxide and some ammonium nitrate. These are both solids. When I mix them together, they're gonna react, and this flask is gonna get really cold. Okay, now I'm gonna prove that it gets cold, hopefully. It's gonna freeze to the box, and I'll be able to demonstrate that to you. But you'll also be able to see that it gets cold because the glass will get frosty and stuff. So this is my question. I want you to think about this, don't say anything yet. Is this reaction endothermic or exothermic? How do you know? And what has to happen at the molecular level in terms of bonds that are forming and breaking for a reaction to be endo or exothermic? Okay, so which one do you think it is? And what's happening at the molecular level that would make it that way? Think about that for about 20 more seconds, and then I'm going to have you talk to your neighbor. Okay, that wasn't 20 seconds this time, but go ahead and talk to your neighbor. I'm just going to give you 30 seconds to talk to your neighbor. What do you think, endo or exothermic? And what's happening at the molecular level? On your mark, as I go. They're thinking this is endothermic. Who wants to tell us why? It's releasing heat. Why do you think that? So if their temperature is decreasing, then they must be releasing heat. Okay? Because that makes it colder when it releases the heat. Okay? What about people who think this is endothermic? Yeah. Yes, you.
Yeah.
Who had your hand on your nose?
I guess they do that in Asia. I think it makes a lot of sense.
Oh, really? Good.
I think since the reaction takes in energy from the surrounding loses heat and becomes colder. So we see that the surrounding is colder, so the endothermic.
Okay, so he says endothermic because the reaction is happening inside the flask, and the flask is getting cold, so like if I were to touch it, let's see if it's frozen. What do you think? It might work? I did it! Yes! Okay. Yes.
I think the reason it's getting cold is because the energy is taken into the surroundings is being stored in the form of chemical bonds. So that's why you don't feel it as heat, because the energy is being moved somewhere else.
So it's endothermic. Because it's endothermic, it's pulling energy in from the surroundings. That's why it feels cold to the touch. My hands are the surroundings, right? So it feels cold because it's pulling the energy in. And where's the energy going? It's going into potential energy in chemical bonds. Okay, good. Enthalpy, right? Good. Okay, so this one is in fact endothermic. A key idea here is to understand what is the system and what is the surroundings, right? And the system in chemistry is basically always going to be the chemical reaction, right? So everything else in the world is the surroundings. And so in this case, the flask, my hands, those are all surroundings, okay? If you understand the direction of system and surroundings, then it makes it a lot easier to decide if it's endo or exothermic. Okay, so what is thermochemistry? We're studying changes in thermal energy due to chemical reactions. Exothermic reactions are going to release heat because the products are more stable than the reactants. And endothermic reactions are going to absorb heat because the products are less stable than the reactants. So we didn't talk about that part. What about the stability? So she said, tell me your name.
Maggie.
Maggie said that the energy that's going in is going into chemical bonds. Okay? So what does that mean about the stability of the bonds that are forming and breaking? I start with my reactants. Let's say my reactants are here in energy. If I have an endothermic reaction, what would my reaction diagram look like? If I start here, where will the products be? She says it'll be higher. They're making like rocket gestures. It'll be higher, okay? So it'll be like a hill, and then we'll have higher energy at the end. Everyone remember these? Yeah? Endothermic? I'll draw a picture. A reaction coordinate diagram. We're going to talk a little bit more about these later today. So, what about the relative stability? Which one is higher in energy, the reactants or the products? The products. And what does high energy mean in terms of stability? Less stable, okay? So endothermic reactions have products that are less stable than the reactants, and exothermic reactions vice versa. Okay, we can measure the heat that's released in a chemical reaction or absorbed using a calorimeter. So that's what we're going to do in class today. What are some examples of thermochemistry that you've seen in your real life? Like, where does stuff like this happen?
Ice packs.
Ice packs, good. Yes.
Campfire.
A what?
Campfire.
A campfire, any kind of combustion, right, is like exothermic, yes.
The refrigerator.
The refrigerator, yeah. So in the refrigerator, it's not actually a chemical process that's happening, it's a physical change for the refrigerant, but yeah, it's one thing is heating up and another is cooling down, yes. If your soup is too hot, you could put ice in it. Who has that problem? Do you have that problem?
You're wrong. It's too hot.
Do you guys who has put, just out of curiosity, ice in their soup before? Oh my gosh, this is so surprising. I feel like my soup is never hot enough. Okay, so but yeah, you can put ice in your soup. Okay, fascinating. Okay, sorry, that was an exciting topic. Okay, other examples. Who has never put ice in their soup? Yeah, so it's like sort of 50-50 here, I think. People who have never put ice in their soup, have you thought about putting ice in your soup, or have you like never thought about that before in your life? I've never thought about that before in my life. Okay. I learn something new every day, right? Okay, good. So, another example is evaporative cooling, like our sweat cools our body down because as the molecules evaporate, they take heat from our body, right? So that allows us to cool down. So this is really relevant in a lot of situations that you encounter in your daily life. Okay, we're going to look at a reaction coordinate diagram. This is like sort of a typical reaction coordinate diagram. This is, we'll pretend that this one is for hydrogen gas combusting. Okay, now who has experienced a hydrogen balloon in a chemistry class? Like your professor about the hydrogen balloon? Yeah? What do you guys remember about that experience? It makes a really loud boom. Do you guys agree with me? It makes a loud boom. And the reason it makes the loud boom is because the reaction is happening very fast. So the speed of the reaction is what makes it have the boom sound. Okay? And what about, did you feel like it was hot when you had a hydrogen balloon? It was maybe a little bit hot. But usually people like in the back of the lecture hall like probably can't feel the heat from it if you have a hydrogen balloon. Okay? So that's for This one is for hydrogen, H2, burning hydrogen. I have a balloon here, and instead of hydrogen, this one has ethane. Ethane. What's ethane made of? C2, H6. C2H6. Everyone with me here? Okay, C2H6. And ethane is in here. This is my question. We're gonna blow this balloon up, and I want you to pay attention to the observations, particularly regarding sound and heat. Can you do that? Okay, and then we're going to talk about how the reaction diagram would be different. Okay, I'm going to turn the lights off for fun. I'm going to get fun news today. So I'm going to turn the lights off, and I'm going to need you guys to count down. Count down, and 3, 2, 1. Okay. They're like disappointing. Okay, you may have noticed some things, like who thought that was a really big boom? Kind of not the biggest, okay. And what about heat? Who felt the heat from that balloon? So people all the way like in the second to the last row here felt the heat from that balloon, okay. So now, this is what I'd like you to do is I want you to find a partner to talk to. One of you will be partner A, one of you will be partner B. Everybody needs a partner. Does everyone have a partner? Raise your hand if you don't. We'll find you one. Can you use a partner? Who can be a partner? Nobody? You need a partner? He's a partner. He's a partner. In the back? Right there. Okay, good. Okay, now, partner A. This is the question, you guys. Okay, we're going to do a thing called paired verbal fluency. We have partner A, we have partner B. This is how it works. Partner A goes first. They're going to talk for 30 seconds. I'm going to say switch, then partner B is going to talk. While partner A is talking, partner B listens and thinks, okay? And then when partner B starts talking, they can continue where partner A left off. They can ask a question about something, they can correct something that wasn't quite right. Just continue the conversation, okay? And partner B will have 30 seconds to talk. This is the question. If this is the diagram for hydrogen, what do we think the diagram would look like for ethane based on your observations? So you should have evidence to support your claim. Are you ready? On your marks, get set, partner A, go! Yes.
Okay, so two things that I noticed in so relative reactants will keep the states at the same way, the same spot. The peak is going to be different because it looks like the reaction happens slower.
Okay, so in what way is it different?
It would be, one is it would take more space this way, and also probably be higher because it's going to take more activation energy if it's a slower reaction.
Okay.
And then also if it lets off more heat overall, then the delta H has to be of greater value, and so the products are going to be quite a bit lower than the products are in the
Okay, so he says two things are different. One is it's going to be taller, the activation energy is higher because it's a slower reaction. Who can tell me what evidence that we saw would support that claim? What evidence did we observe when we did this reaction that supports that claim? Yes?
The heat that everyone can feel, like
Okay, does the heat, being that everyone can feel a lot of heat, affect the height of my reaction coordinate diagram? Is that the thing that it affects?
no.
What is it that it affects?
The length.
Spread. Or how
Or how low.
right? How exothermic it is, right? So that evidence that the heat was all the way to the back is supporting the claim that it's more exothermic. Okay, so it would be like longer this way, more energy between the reactants and products. And you had a hand? Yes.
I was just say the sound was softer than the hydrogen cooling,
Uh-huh.
and so that would suggest that it was a slower reaction, which would then higher activation.
Okay, good. So the sound that we heard was a softer sound, and the boom happens when the reaction happens very fast. And so since we have sort of a softer, like less exciting boom, then we know that it should be slower, and that's what causes this increase in the activation energy in the reaction, or it's associated with that. Does that make sense? Yeah? Are we like scraping the back of 105?
Yep.
Is that what's happening? You're like, I think I learned about this one. Okay. Okay, so here's a couple of diagrams that we can look at. The degree to which something is exothermic is going to depend on the distance vertically between the reactants and the products. Okay, or if it's endothermic, it would be the other way. And how fast it happens has to do with the size of the hill. Like this first one has a very tall hill, which is our activation energy, which means it's going to be a little bit slower. So if we were making a graph for ethane, if we had hydrogen, we said it might look like this. And if we had ethane, pretending they're starting in the same place, it should be taller and lower. Okay? This because it's slower, as evidenced by our less boom. This because it's more exothermic, as evidenced by the heat that everyone felt. Okay. Good. So today in class, you are going to do an experiment with calorimetry. I don't have a laser today because they locked all the drawers. So I can't point at anything. I feel sad. I can use this. Okay. This is your reaction that we're going to do today. What's this box here? It's like our calorimeter. For us, it's just actually a cube of styrofoam. Probably like 30-year-old styrofoam. Yes. Okay. Fancy because it's just the right size. It has a hole in the middle. It's just the right size to fit our dram vial in there. Okay? Which is sort of like a beaker, but it's just real small. And flat on the bottom. So we have our dram vial, and that's where we're going to put our reactants. Okay? What is the system and the surroundings here? Tell me, what do you think? Yeah. System and surroundings, what do you think? I didn't hear. Okay. So like the calorimeter and the dram vial, those should be part of the surroundings. Okay, good. What else is part of the surroundings? Yeah.
You should be inside the intake little box that takes in the air.
Okay, we don't have any air here. Not fancy calorimeter. Not a bomb calorimeter. We have styrofoam, you guys. I'm sorry. But then that would be maybe part of the surroundings if it were here. But we don't have any yet.
The stuff that the aqueous materials are in solvents, probably water.
Okay, so actually this is an important idea. The surroundings include all of the solution, okay, like the water that's in our dram vial. If that's true, what's the system? Yeah.
The reaction.
Just the reaction, just the chemical reaction. So if you're looking at it, you can't actually tell the difference between the system and the surroundings. They're both inside the Dram vial. Okay? Because we're making the assumption here that no heat is lost to the vial or the styrofoam or the air or anything else. Is that a good assumption? Probably not great. Especially our like 30-year-old styrofoam cubes, okay? But the system is the chemical reaction. The surroundings are the solution in which the chemical reaction is taking place, okay? So the system, the chemical reaction, has heat associated with it. It's exothermic, so we have Q, which is our symbol for heat, right? I can't reach that far. Q. Okay, I won't try. It's not funny. Q equals N delta H. Have you seen this equation before? Yes. Good. Okay, what is N? Number of moles of reactant, the limiting reactant. Okay. Divided by what?
Stoichiometric coefficient.
The stoichiometric coefficient. Okay, so it's number of moles divided by the stoichiometric coefficient. For example, if you used 0.2 moles of the 1:4 ratio or the 4:1 ratio, you have 0.2, you would divide by 4, which is the stoichiometric coefficient, and then you would get 0.05 for N. Why are we doing this? Just to torture you? Yeah. No. It's because we want to know the delta H for the overall reaction as written, not per mole of the stuff that we're talking about. Okay, so we correct for that so that we get the delta H for the whole reaction. Does that make sense? Okay. Okay, good. It helps me if when I ask you like if something makes sense, if you could do one of two things, like nod and smile like it makes sense, or shake your head no, like I feel confused. And then I can help you. But if you just stare at me, then I don't know. So are you good with N? Why do we have to divide? Because I need what? Moles of? Yes.
I'm sorry, where can we get the stoichiometric coefficient from?
It's going to depend on which unknown you have. It's either 1, 3, or 4 in this experiment. Does that make sense? Yeah. Good question. Now, what is N? Why do I divide by the stoichiometric coefficient? Because I want what?
Number of moles for the ratio. Whole reaction.
I want the whole reaction, my delta H for the whole reaction, not my delta H per mole of that stuff, which is why I'm going to change that. Okay. So we also have the surroundings. The surroundings are the solution. The solution is Q equals MC delta T. You guys have seen this before, yes?
Yep.
Now tell me in this experiment, what should my M be? I heard somebody over here say mass. Did somebody say mass over here? Mass? Okay, mass of what?
Of the reactant. Whatever is the capacity.
Okay, she says I need the mass of whatever it is that I have the specific heat capacity of, which is like a really good way to answer the question when you're not quite sure what is the mass of. Don't you agree? Yeah, because that's totally true. I need the mass of the thing that I have the specific heat of. Now, what do I have the specific heat of? The water, or the solution, okay? And so, in fact, the mass is going to be 10 grams here for your trials because you have 10 milliliters of your solution. Okay?
So it's going to be 10.
So it's going to be 10. Okay. I should clarify, it will be 10 if you are measuring your volume exactly and it's 10.0. If you have some other volume, you would have to change that, but you shouldn't have some other volume. Okay. We've got C, which is specific heat for water. We've got T, delta T, which is our change in temperature. We add these together and they equal 0. Why? Law